Hello, I am Professor N.K. Pandey from Department of Physics, University of Lucknow. And in today's session, we are going to talk on carbon dioxide lasers. Now, the carbon dioxide laser was one of the earliest lasers in the infrared range. The principal wavelength bands they center on 9.4 micrometer and 10.6 micrometer. Carbon dioxide laser was invented by Mr. Kumar Patel of Bell Laboratory way back in 1964. CO2 lasers are the highest power continuous wave lasers. This laser gives pulsed energy of 10 kilojoule and continuous wave power of the order of 100 kilowatt. They are highly efficient. The ratio of output power to pump power can be as large as 20%. Now, what is the amplifying medium consisting of in a carbon dioxide laser? Now, in the discharge tube, the gas mixture consists of 10 to 20% carbon dioxide, 10 to 20% nitrogen, some percentage of hydrogen, and or xenon, and the remainder of the gas mixture is helium. The specific proportion of these gases may vary according to the use of the laser. Now, the oscillations between two vibrational levels in CO2. Actually, this laser is based on the oscillations occurring between two vibrational levels in carbon dioxide, while the efficiency is improved by the presence of nitrogen and helium. The population inversion in the laser is achieved by the following sequence. The electron impact excites the vibrational mode quantum state of nitrogen. Nitrogen is a homonuclear molecule, hence it cannot lose this energy by photon emission. And its excited vibrational modes are therefore metastable and relatively long-lived. N2 and CO2 are nearly resonant. The total molecular energy differential is within 3 per centimeter. N2 de-excites by transferring through collision its vibrational mode energy to the CO2 molecules, causing carbon dioxide molecules to excite to its vibrational mode quantum state. Now, this is the energy level diagram for a carbon dioxide laser. As we can see, through the pump, we excite the atoms of nitrogen, which through collision pass on their energy to the CO2, which makes laser transition at 9.6 micrometer and 10.6 micrometer over here. And from here, they need to be brought down to the ground state to be pumped again. And here, the carbon dioxide molecules, they make transition to their vibrational mode ground state by collision with cold helium atoms, thus maintaining the population inversion. The resulting hot helium atoms must be cooled to sustain population inversion in the carbon dioxide molecules. Now, if the laser is a sealed one, this takes place as the helium atoms strike the walls of the laser discharge tube and cool down. Whereas in a flow-through lasers, a continuous stream of CO2 and nitrogen is excited by plasma discharge, and the hot gas mixture is exhausted from the resonator by pumps. Now, structurally, there can be two types of CO2 lasers. One is longitudinally excited CO2 laser, and the other could be transverse excited CO2 laser. Now, in the longitudinally excited CO2 lasers, the scheme works as conventional gas discharge lasers having long cylindrical narrow glass enclosures with electrodes at both ends, which provide the current for excitation of the discharge. These lasers can operate in continuous wave and pulsed modes both. These tubes can be very long, several meters sometimes. In some configurations, the enclosure of the discharge is sealed. Now, this is the structure of a longitudinally excited CO2 laser. You can see that these are the two Brewester windows here and here, and we have here, this is the gain region, that is the gas mixture is there. The laser beam comes out from here. And you can see from here that this is excited longitudinally. And to see more clearly this one, you can see the block diagram. Here we have the electrodes. The discharge is done in the longitudinal direction through the excitation circuit and power supply. We have the mirror here and the output coupler here. We have a pump here and the gas bottle is here for filling up. So this is the block diagram for a longitudinal excitation system of the carbon dioxide gas laser. In the sealed tube, the CO2 molecules can get disintegrated. The CO2 molecules can break up and produce oxygen, which can result in corrosion of the electrodes. Water vapor is considered to improve the power output and operating life of a CO2 laser. Water produces OH radical in the discharge, which when combined with CO produces CO2 and H. The enhanced output power of CO2, N2, He, H2O, H2 laser is believed to be due to the effective relaxation of lower laser level by impact with H2. Sealed off lasers are compact and portable. The output spectrum is stable. Conservation of costly gas like helium is also possible, because here the helium is cooled by making collision with the walls, whereas in a flow-through discharge tube, the hot gases are taken out of the tube and again filled up. So in the sealed tube, you have conservation of costly gases like helium possible. However, they suffer the disadvantage of having a small operating lifetime. The tube is required to be cooled with water to keep the temperature at about 20 degrees centigrade, because the output of the laser decreases as the walls of the tube becomes hot. Now, transverse excited laser at atmospheric pressure. In this is also called a T laser. In a T laser, atmospheric pressure is maintained inside the discharge. The pressure can be up to 1 atmosphere or greater than that. The gas discharge is maintained by applying the electric field in the transverse direction, as we can see in this figure. We have the power supply, we have the excitation circuit, and this is the tube we have here. And you can see the discharge direction in the transverse direction over here through the electrodes. And as in the longitudinal excited laser, we have the mirror here, we have the output coupler over here, and the laser output direction is this one. The rest of the things remain the same. Only point is that the discharge is taking place in the transverse direction. The advantage is because now the gap is a smaller one. The transverse direction is very small. Therefore, even a small potential difference is able to produce a large electric field for the discharge. And therefore, the discharge can be done very conveniently, even at lower potential difference. Now, the voltage required for transverse excitation is quite less, since the gas discharge occurs at critical electric field. The transverse dimensions are of the order of 10 millimeter, which requires a voltage of about 0.12 kilovolt. The discharge has to be maintained uniform all through the length of the discharge tube. The T lasers operate at a gas pressure of 1 atmosphere or more. The energy output is a function of the volume of the gas. Operating the laser at high pressure with longitudinal discharge, as in the previous case, is very difficult because the operation demands very high voltage for initial ionization of the gas. Moreover, arcing can occur within the discharge, which may make current to flow in random and irregular directions. Because if the electrodes are placed far away, then the electric lines of forces at the ends at the electrodes may be distorted, and therefore the force on the electrons there may be in random directions, making current to flow in random and irregular directions, an undesirable effect that will be there. In a transverse discharge, whereas the electrodes are placed parallel to each other over the entire length of the discharge tube, separated by a few centimeters, and the voltage is applied as shown that we had seen in the figure. Before applying high voltage, a process of pre-ionization is done to ionize the region between the anode and the cathode. This results in filling up of the area with electrons. The pre-ionization enables the discharge to be uniform through the entire electrode assembly, and arcs due to generation of high current is avoided. So pre-ionization is needed. The process of pre-ionization involves flashing of ultraviolet rays from an array of pre-ionizing ultraviolet spark discharge. This ionizes a portion of the gas uniformly between the electrodes. Since CO2 lasers operate in the infrared range, special materials are needed for their construction. Certainly, those materials which are used in the visible range cannot be used over here because it is in the infrared range. The mirrors are silvered. Windows and lenses are made of either germanium or zinc selenide. For high power applications, gold mirrors and zinc selenide windows and lenses are preferred. Diamond windows and lenses are also used. Diamond windows are very expensive, but their high thermal conductivity and hardness make them useful in rough environments and high power applications. Optical elements made of diamond can even be sandblasted without losing their optical properties. However, historically, lenses and windows were made out of inexpensive salt, sodium chloride or potassium chloride. But of course, these lenses and windows degraded on exposure to atmospheric humidity. The basic form of a CO2 laser consists of a gas discharge having a perfect reflector at one end and a partially reflecting mirror at the other end, as we have seen earlier. The second mirror acts as the laser output coupling device. The CO2 laser operated on continuous wave mode may give powers from few milliwatts to hundreds of kilowatts. If CO2 laser is Q switched by means of an electro-optic modulator or an acousto-optic modulator, we may have peak powers of up to gigawatts. Well, let us consider certain applications of CO2 laser. Due to their high power levels and reasonable cost, carbon dioxide lasers are commonly used in material processing applications of cutting and welding, particularly for cutting die boards, metals, plastics, etc. Welding metals such as copper, aluminum or stainless steel, and laser marking of different materials. The lower power lasers are used for engraving also. Carbon dioxide lasers have become useful in surgical procedures because water that makes up the most biological tissues absorbs the infrarange frequency of light. CO2 lasers are often used in laser surgery and skin resurfacing. The laser facelift involves vaporizing the skin to promote collagen formation. The common plastic PMMA absorbs infrared light in the 2.8 to 25 micrometer wavelength band. So, carbon dioxide lasers have been used recently for fabricating microfluidic devices from it, with channel width of a few hundred micrometers. Since the atmosphere is quite transparent to infrared light, carbon dioxide lasers are also used for military range finding using LIDAR techniques. Now, CO2 lasers are also used in spectroscopy, and one special process, SILEX process. SILEX process is a process to enrich uranium, because we know that natural uranium that is found is having a mixture of uranium-235 and uranium-238. The SILEX process exposes a cold stream of mixture of uranium hexafluoride molecules and a carrier gas to energy coming from a pulsed CO2 laser operating at a wavelength of 10.8 micrometer and optically amplified to 16 micrometer, which is in the infrared region. The 16 micrometer wavelength laser preferentially excites uranium-235, creating a difference in the isotope ratios in the product stream, which is enriched in uranium-235, and a tailing stream, which has an increased fraction of more common uranium-238. Thank you very much for your kind attention.